Okay, Year 12. We're going to go through these last bits about supernovae, I should say. Whenever you have an AE on the end of a Latin word, it's pronounced I, so supernovae, and black holes. We already should know roughly what these two things are. We've been through it, we've watched the Kurzgesagt videos. We should be fairly confident with it. If we're not, though, we can have a quick recap. So, higher mass stars have a short lifespan. They can continue fusing elements well beyond helium. The most massive stars take it all the way up to iron, but iron fusion is endothermic, would be one way of putting it. It requires energy to make anything bigger from fusion once you get to iron. So once you start making iron, the star has only seconds to live. The core collapses inwards, and if it's a smaller star, then we don't get a supernova. We just end up with a white dwarf where electron degeneracy supports the core of the star. However, if the core is more than about 1.4 solar masses, which is called the Chandrasekhar limit, then unfortunately, strange way to put it, electron degeneracy can't stop the collapse, so it collapses further. The core is collapsing inwards, the outer layers also fall inwards at about a quarter of the speed of light, and they rebound off the core, which produces this huge shockwave, this huge explosion, which we call a supernova, leaving behind a neutron star, or, if the core was more than about 3 solar masses, then a black hole. There is a video from Brian Cox, yet another one. I'll link this rather than watching it now. It is a pretty good video, if we didn't already get enough from the Kurzgesagt ones. Not required to watch, though, if you think you have the information you need. This is our definition at A level of a supernova, and it's a bit of a strange one. A supernova is a rapid increase in absolute magnitude of a star. That's how we determine that there's a supernova. There's a rapid increase in absolute magnitude, and therefore a rapid increase in apparent magnitude as well, because it's still the same distance from us. In terms of brightness, the power output, the brightness of the luminosity of a supernova can briefly outshine the entire galaxy that it's in. And this is a fact that we do need to know. They will ask you to recall it. A gamma ray burst, or indeed many supernovae, will produce more energy in a few seconds than the sun will over its entire life. So that's the comparison we need to make. The entire lifetime of the sun versus a couple of seconds of a supernova. This is an animation showing the SN 1987A. So this is the best studied supernova ever. It was the first one, really, that occurred in the modern era, and we had telescopes looking at it. So there was a supernova, and we've been able to actually track the expansion of the debris from the supernova over time as it gets ejected out into the interstellar medium. And this is a picture of that over the years, and also at the end that 3D rendering showing the shape of these remnants that are going out into the rest of the galaxy, where they'll mix with the rest of the hydrogen and eventually will come and form the next generation of stars. So again, a supernova is recognized as a sudden, rapid increase in the magnitude of a star. The actual supernova takes seconds, but there's an afterglow. We see the clouds for a relatively long time. And you can have a look. There's various different types of supernovae. There's only one type that's really important to us. The type 2s are just the standard ones. The type 1As are the ones that are really, really important. This kind of graph is very, very important. This is a light curve. It shows how the absolute magnitude of the supernova varies relative to the day of peak luminosity when it was at brightest. So that 0 is not the start of the scale. We actually have some time before that. So the first instant of a supernova is not the brightest second of it. It's actually brighter a little bit further down the line. So, like I said, Type 1a supernovae are the most important ones for us. And they occur when you have two stars in a binary system. One is a white dwarf, and the other one is another kind of star, probably a red giant. The white dwarf begins accreting matter, begins stealing matter from the other star. And white dwarfs are not fusing. But when it reaches this very specific critical mass, then all of a sudden, carbon fusion occurs again. And this runaway reaction takes place. It's not in hydrostatic equilibrium at all, because the only thing that was keeping it in place was electron degeneracy. This is not quite the same process as what happens in a normal supernova, but it is happening at a similar mass. So remember, if the core was more than about 1.4 times the sun's mass, then you'd get a supernova. This is slightly different, but same sort of idea. Because it happens at this exact critical mass, the same tipping point, it always has the same luminosity, the same absolute magnitude. A Type 1a supernova is always the same brightness. And that's really important, because it means that it's something called a standard candle. We'll get into a bit more detail in a second, but standard candle is exactly what it sounds like. It's a light source, a candle, and it is standard. It's always the same. It's something that you know the brightness of for sure. If we look at the light curve for a Type 1a supernova, it has a very specific shape to it. It's different to these curves from the other types of supernova. So whenever you see this shape, we know you have a Type 1a supernova. And if you know you have a Type 1a supernova, you know that you have your peak absolute magnitude or luminosity of minus 19.3. About 20 days after the start. So try to remember those numbers, minus 19.3 and 20 days after the start, because you might be asked to sketch this. Now, how far do we continue it on? Well, you see different graphs. Sometimes you'll be asked to continue it on to 80 days. Sometimes, like this one, all the way on to 300 days. It really depends on how long you want to record this for. That will change the apparent shape of the graph. We'll have a look at a few questions later on, but remember it's got this sharp peak up to minus 19.3 after 20 days, and then a relatively quick fall away for another 20 odd days, and then a slightly slower decrease thereafter. It's because we know what different isotopes are decaying, basically, causing this light curve to be as it is. If we know absolute magnitude, we can measure apparent magnitude by comparing it to other objects. And remember, from the equation we've used so many times already, if you know absolute magnitude and you can measure apparent magnitude, you know the distance to the star. So this can be used to work out the distance to a galaxy that's a long way away by working out the distance of the supernova that occurred inside that galaxy. Again, just a bit of a recap about neutron stars. They're the result of a supernova that is of a medium-sized star, so the core is 1.4 to 3 solar masses. I'll link to a story from the BBC about an interesting intermediate that was found in the last few days. The neutron star is left behind, typical density about 4 times 10 to the 17 kilograms per cubic meter. So it's basically nuclear material, 20 odd kilometers across. I remember it as the size of a city, and they rotate very fast because of the conservation of angular momentum. As they contract, they start rotating more quickly. They emit radio waves in 2 beams, and they come out of each pole, basically. And sometimes, if they're at the right angle, they sweep past the Earth periodically, and those are observed as radio pulses. That means that some neutron stars are known as pulsars, the ones that have these radio beams pointing at us. Now, this is where we need to learn a little bit more. We know that black holes are the end stage of a very large star, but we need to know a little bit more about it. So the first concept that we'll explore far more when we do gravitational fields is escape velocity. So if you took a tennis ball and chucked it into the air, it would come back down. If you chucked it much harder into the air, it would take longer to come back down. But, assuming it was an indestructible tennis ball, if you chucked it hard enough into the air, it would never come down. It would have enough kinetic energy to escape the gravity well of Earth. It has sufficient kinetic energy to get all the way to infinity, to never come back down. That's escape velocity. And your escape velocity basically depends on the density of the object that you're on. So, an object like a black hole has a very high escape velocity. In fact, it's higher than the speed of light. Nothing, including light, can escape from a black hole. The boundary of a black hole is considered to be the event horizon. So that is the distance from the black hole where the escape velocity gets larger than the speed of light. So inside the event horizon, nothing can escape. Just outside the event horizon, photons can escape. It's the defining boundary of the size of the black hole, if black holes can be considered to have size at all. You may be asked to calculate the Schwarzschild Radius. This is the radius of the black hole. It's the radius of the event horizon. It's pretty straightforward. Inside, nothing escapes. Outside, light can escape. Or a physical object with sufficiently high kinetic energy. This is the equation we need to use to calculate it. Schwarzschild radius, in meters, is equal to 2 times big G, where big G is the gravitational constant in Newton meter squared per kilogram squared. Bit of a mouthful on units there. Multiplied by the mass of the black hole in kg, divided by the speed of light squared in meters squared per second squared, or the speed of light in meters per second squared. Okay, have a go at this question now. Pause the video, and we'll have a look to check that we've got the right answer in a few seconds. Okay, check your answer, make sure that you followed the right method, and you got the right answer. Your working should look something like this, and you should have got something on the order of about 9 kilometers. Pretty small. And don't forget, always round your answers to the same number of significant figures that you've been given data to. So in this case, 3 significant figures. 8,890 meters. Second question, remember that sometimes you'll be asked to do some fairly arbitrary random looking calculations on stuff, so this has got nothing to do with black holes really, this is just, can you logic your way out of it? Again, pause the video, have a go, and then we'll check the answers. Density is mass divided by volume. We need the volume of the black hole. So, on the front page of your formula sheet, if you didn't remember it, you have the formulae for the volume of a sphere. So it's 4 over 3 pi r cubed. So our volume is 2.95 times 10 to the 12 cubic meters. Once we've got that, density is mass divided by volume. And we should get out 2.04 times 10 to the 18 kilograms per cubic meter. To 3 significant figures. Let's go through and have a look at what we have covered today that perhaps we didn't necessarily know before. Type 2 supernovae are caused by stars collapsing. The luminosity depends very much on the mass of the star. More massive star, brighter supernova. However, Type 1a supernovae occur when the accreting white dwarf reaches around 1.4 solar masses. Always. So they have a standard luminosity. The shape of the light curve is predictable, so that means we can identify them easily. And that means they are standard candles. We can use them to determine the distance to them from the luminosity-distance relationship, the relationship between absolute and apparent magnitude and distance. The Schwarzschild radius of a black hole is the distance from the black hole, where the escape velocity is equal to the speed of light. Yes, black holes are the only objects that have an escape velocity greater than the speed of light. And the formula for calculating the Schwarzschild radius is Schwarzschild radius is equal to 2 times the gravitational constant times the mass of the object divided by the speed of light squared. Have a go at some of these questions. In addition to the past paper questions, we will go through them on Friday during our Q&A. If you can attend, I know you'll be in lesson. If you have other subjects that you need to do or your teacher's teaching you, that's fine. But if you can attend, and there's an opportunity to do so, please do. And this is the second set of questions I'd like you to try. Some of them might require research because we haven't necessarily mentioned everything here. You might know it from your general knowledge though. Again, we'll cover this on Friday if we have any difficulty with any of it. Thanks guys. Do finish up those past paper questions as well, and I'll see you on Friday.